We're surrounded by displays that cater to our sensory modalities. Most are visual and auditory. Tactile and force displays have become more common. We even have super specialized ones that display temperature, taste, and olfaction. However, one sensory modality remains a challenge to represent: kinesthesia, the sense of movement. But what if you could experience movement without actually moving? With motionless movement, we transform force applied by users' non-moving limbs into an experience of movement as a first step towards kinesthetic displays. My name is Yu Randing, and I'm presenting this work done together with Nihar Stavnes and Paul Strohmeyer at the Sensory Motor Interaction Group at Max Planck Institute for Informatics. Current efforts to alter kinesthetic experiences implicitly include body distortions and redirected pointing. These techniques have been relying on visual and acoustic cues. However, we believe that using the sense of touch may lead to a more embodied experience of movement. Also, cutaneous senses are considered important kinesthetic cues. While researchers have been able to induce kinesthetic illusions through vibrotactile stimulation of the tendons, the magnitude of these illusions is low, and they're not easy to consistently elicit. It is unclear to us how or even if these can be systematically used in an HCI context. In HCI, directly inducing a sense of body movement in a user is typically achieved by either grounded force feedback or electrical muscle stimulation, EMS. However, grounded force feedback devices are restricting the users to a fixed location and are bulky and expensive. EMS, on the other hand, has been used to directly actuate users to move in the real world. This makes EMS less favorable in contexts where movements are not so convenient. We propose to overcome these drawbacks by using a friction rendering approach to represent movement. This is to create an illusion of the friction experience during movement through synchronized haptic grains. We designed a haptic feedback device that translates force input into synchronized vibrotactile signals. Users experience movement through grain-based vibrotactile feedback. We call it the Motionless Movement Kinesthetic Display. This device induces a sense of movement in users, even though their hand remains motionless. We achieve this by looking at the literature of grain-based vibrotactile compliance solution through another angle. For these compliance solutions, sensors first sense the magnitude of pressure the users applied on the object. The sensor signal range is then divided into a number of discrete beans. When a sampled signal value changes and enters a new bean, a vibration pulse with a designed waveform, duration, amplitude, and frequency is generated. When the signal changes fast, pulses are generated rapidly. When the signal changes slowly, pulses are generated proportionally slowly. The number of beans corresponds to the overall density of pulses in the sensor range, and aka granularity. These haptic vibration pulses, or grains, give an illusion of friction coupled to user action. The user then perceives the rigid material they are interacting with as receding under their pressure. While most literature focuses on the perceived change in material, we believe that there is a second phenomenon being overlooked. For the user to believe that the material they are pushing is deforming under the pressure of their finger, they must also believe that their finger is moving. In other words, when experience a vibrotactile compliance solution, users believe their finger is moving even though it is not. We then leverage this phenomenon to change the direction of the movement experience. So instead of feeling the movement of the finger pressing down, our device induces the feeling of moving on the plane. Our kinesthetic display forms a closed-loop feedback system with the user, taking input from users' efferent pathways and giving output to users' afferent pathways, creating sensory-motor contingency. Here's how our kinesthetic display works. Users provide pressure on a stationary metal handle, like they're pushing a handle in real life. The pressure input detected by load cells is then processed through a microcontroller and transformed into grain-based vibrotactile signals and visual rendering. Finally, users experience this integrated movement feedback through haptic sensations and virtual reality renderings. A closed-loop perception augmentation device is formed with the user as part of the system. We explore the design space and movement perception of our device using 4 studies, with each study building upon the previous. So, let's dive in. In Study 1, we investigate how haptic mapping method might affect perceived magnitude and naturalness of the movement experience. This is to identify a desirable mapping that induces embodied movement experiences. We investigated different vibrotactile mappings, with 3 grain-based vibrotactile mappings and 1 constant vibration. The 3 grain-based vibrotactile mappings couple vibrotactile pulses to different parameters caused by user action, such as pressure and simulated distance. Our first mapping is pressure-based. Here we take the magnitude of instantaneous force in the direction of movement. Here's our interaction and how the vibration sounds. The second mapping is distance-based mapping. Using a simple movement simulation, we transform the force signal used in the first mapping to a position. We couple grains to this virtual position, creating an experience of grain-based friction illusion along the simulated movement path. A concern we have with this distance-based mapping is that movement onset and the endings of movements might feel not compelling. To address this, we created the third mapping, hybrid mapping. This uses a pressure-based mapping up to when the force in the direction of movement reaches a small threshold, a value that matches the force needed to overcome the static friction for moving the selected object on the desk. When forces exceed that threshold, the mappings become distance-based. Finally, for reference, we also created a mapping which simply displays constant vibration when force is exerted. We asked our participants to rate the strength of movement and naturalness of the experience for each mappings. We standardized the estimates and computed 95% confidence intervals. On the left is the result for the strength of movement, and on the right is people's rating for naturalness. We found that our hybrid and distance-based are rated to have the strongest movement experience while being most natural. Distance-based and hybrid mappings are often associated with embodied movement experiences in the physical world, such as textures and frictions. P6 felt like going over a bumpy surface very fast. P8 felt friction, the ball is moving really fast. Constant vibration is also rated to instigate the strongest movement, yet it feels so very unnatural. P10 mentioned that he can move very far, but it doesn't feel natural at all. The vibration is way too regular to associate it with any surface. It starts to feel like a machine. When I push it, it vibrates. Pretty interesting, right? Perhaps participants just interpreted vibration symbolically as an indication of movement, instead of feeling embodied movement with the constant vibration. Now, let's move to study 2. After finding out the desirable haptic mapping method in study 1, which are distance-based and hybrid mappings, we conducted study 2 to understand how granularity of the desirable haptic mapping might affect the magnitude of perceived movement. As we talked about, granularity is the number of bands on the y-axis of this figure that corresponds to the overall density of pulses. Both distance-based and hybrid mappings are pretty good at giving natural movement experiences. We applied Occam's razor and went with the simpler algorithm. Using magnitude estimation of perceived movement of 3 granularity levels, we found that a higher granularity of vibration pulse corresponds with larger perceived movement, with declining yields. Then we progressed to study 3. In study 3, we added visual feedback in virtual reality to the experience to identify if and how haptic granularity would be matched to the magnitude or gain of visual movement. In particular, what visual mappings would seem just right for the corresponding haptic granularity. However, no clear pattern emerged after we standardized the estimates and calculated the mean and 95% confidence levels. Finally, Study 4 further builds on Study 3. Remember that in Study 3, participants are asked to find the visual haptic match that feels just right to them. In Study 4, with the same participant and same visual haptic match, we investigated the effect of visual renderings on the belief in embodied movement. We perform a magnitude estimation on the belief in movement with experiences using 4 conditions: both haptics and visual, haptics only, visual only, and none. Combining haptic and visual feedback performs best. Haptic feedback alone provides strong belief in movement that it outperforms the experience provided by visual feedback alone. This essentially means that, on average, people focus on tactile feedback over visual feedback when reflecting on how convincing the embodied movement experience is. Participants commented on the visual-only condition as not as embodied. It's this similar feeling to when you use a computer mouse, like, okay, I feel like I'm moving, but it's not like it's my hand. Obviously, like translating my movements into something else. It was also a pleasant surprise to see how combining visual and haptic feedback creates a best of both worlds kind of situation. This result also suggests that, hey, our method is able to induce a stronger illusion than previous work that relied on visual feedback only. Pretty impressive, right? Our results show that our device provides a natural movement experience, and that it points towards a future where kinesthetic displays might be used to show what a movement should feel like. For example, it can be applied in the field of rehabilitation, sports, virtual reality, and beyond. Please see the paper for more details. You're also welcome to contact us for any inquiries. Thank you.